Okay, let's continue. Can you hear me? Good. So I'm going to talk a bit about distributions. So in the books, I think it's chapter 9 or something. I'm not going to say more than that, even in fact less than that. So distributions. So the distributions are something which should be very natural in physics. So take some, suppose you have some, say, an electric field in some region, so at every point you have a E vector, and you want to measure it, and what really you do is to take a region, just say a point. If say you want to measure the voltage or something, you take a region here, you put one of these points on the tester, and you put some other here, and you measure. And you are never measuring points, so you are measuring regions. So it's natural, instead of measuring the E, you measure the E with something, where this is integral. So actually what you have then is a map from the space of vector in some Hilbert space to the reals, and you map it with some things which are infinity in general and of compact support. So when you do this pairing, what you are thinking is, okay, this I call a space D, and the space where these things lives is D prime, the dual space. So you try to think that way. So the things you measure are numbers, and the numbers you are measuring is these numbers that you have here. So you can work in this way, okay? And of course, if you have two, and why we use a dual or not something more complicated? Because if you have two fields, for instance, say, and you want these things to be the sum of E phi plus alpha E twiddle of 5. So if we are in vector space, it's normal to use the dual directly. So you say, okay, my test function, these are the test functions, are things which are infinity of compact support, and the dual space is the dual in the sense it's a dual in some topology, right? The things here are not anything, but has to be in some topology. And here there is no scalar product, there is no norm in these spaces, because this space doesn't have any norm. So this space is not a Banach space, because we cannot put a norm that controls every derivative, but is a nice vector space and has some topologies, some weak topologies, and we are going to see, not today but later, what we use here. So this is it. So let me go to the, maybe it's better I go to the book so I don't have to write so much. Let me see if I find. I didn't prepare this thing, so I want to have something so that I don't miss something. I have to go back and forth, etc. Here it is. I have the weak compactness. So this is what we say, okay. We are going to take this infinity function of compact support. So those are functions which are are smooth, no, infinity, and only have are different from zero in some compact region. Okay. So it's the support of a function is all the places where this function is not 0 to the minus 1, and you take the closure. So the support is always a closed set. And so here we are saying this closed set is bounded to, so it's compact. And in these functions, they form an algebra, right? If you add to the function of compact support, you get a compact support function, so it's a vector space. But if you multiply them, you get also a function which is of compact support. So it's more than a vector space, it's an algebra. And so here is the convergence notion that we have in this space. So we have a sequence here. Here we don't have norms, so we don't have Cauchy sequences. So we have to say when something converges in a different way. So we take a sequence of elements of this space, and we will say that this sequence converges to phi if there is a compact region, so that the support of all these functions is inside of K. And also we say that the sequence of all the derivatives converge uniformly in K to the phi p. That is, if we take in the support, we take this difference less than epsilon, okay, for n big enough. And here we have a unique n for all the points x in K. But p can be different, right? The n for p can be different. This is to avoid the following thing. I can have a sequence of compact support, so something like this, and this is element 1, the element 2 is some element which comes like this, and the element 3 is something like this, So it's a compact support function which is moving away, okay? So this converges to the function 0. If you don't require this thing converges to the function 0. And we don't want this to call a conversion sequence. That's why we say, okay, they can escape some region and then they have to be there. That's why we require this condition. So there are actually two conditions. There are the uniform continuity convergence of every derivative, and that the support is fixed. Okay. So this is a convergence, and that defines a topology. And now we want to say what is a continuous function in this topology. And then we will say like this. So a functional f from these equations to the real or to the continuous is continuous at some value, at some function phi. If given a convergence sequence phi n to phi, it holds that these numbers converge. Okay. So notice that here you have to say that phi n converges in the way we said before, and then continuity is just the right thing. Okay, if this something is continuous at this point, if I have a sequence approaching this point, then the limit of the sequence is the value of the function at this point. And so this space infinity then, C0 infinity, with this topology, so with this notion of continuity and convergence, is a topological space, and this space is called D. Okay? And it's the space of test functions. Now, since we have this definition of continuity, we have the dual, the continuous dual. So the space, the dual space, D prime, so it's a space of linear continuous functionals T from this space to R in the topology that we just mentioned, is called the space of distributions. Okay? So let me give you some the trivial examples. If you have a continuous function, you can take this functional T of f, which is just the integral of f times 5 in the reals. Okay? And we have the following things, since the norm of this, the absolute value of this number is you can bound by the absolute value of the integral of this times the supremum of phi. Okay? So, and this is bounded because it's in this space, and so this is bounded because it's a continuous function. Okay? So this is a number. So any continuous function give me a distribution this way. And you can show, for instance, that if I give f and g to different functions, then the distributions are different. for continuous. But you can take f to be just integral in the sense of the Lebesgue measure, for instance, and then you will have this functional the same, and this you can bound this the following way. You take the supremum of this and this integral as before, but since this function is integral, this is also bound, is a constant, so you get a bound also for integral functions, right? So integral functions also produce distribution. So these things prove that this why this, how do we prove continuity from here? This is because it's bounded, simply because if you take a sequence that converges, then Tf of 5 minus phi n, this is a sequence, is less supremum sur on A between k in k of 5 minus phi n times this integral. This is just a number, and so since we are saying that this sequence converges to some phi, then there is a k which contains all the support of this, and so we have this is compact, so this support is finite and go to 0, and so that tells me that T of f of phi n converges to, because this becomes smaller and smaller, to Tf of phi, and we have the continuity. So every time you get something, some bound like this, you have continuity. But let's see that there are, so functions which are integral are distributions, but there are things which are not functions. So let's consider this. For instance, t of some point A is given by this. T of A of phi is phi evaluated at A. So this map is linear, because if I take a linear combination of test functions, this will give me this, and this in turn is just this. Okay, so it's a linear space, it's a linear function, and it's bounded because Ta of phi is phi of A, which is bounded by the supreme. Okay, so this is a nice distribution, and it's called the Dirac delta. Okay, so the Dirac delta, which we call x minus I usually, is not a function, this, but it's a distribution. And you can see that there is no continuous function, which this is not equal to the t of some continuous function. Okay. And in fact, any comes from any measurable function. Okay, so this is called a irregular distribution. It's a distribution that doesn't come from continuous function. So distributions are not functions, are some vector space which is bigger, but on which we can define many things. For instance, in some cases you can define products. For instance, this is a product of a distribution times another distribution that comes from a test function, and this is just defined like this. So the action in this test function of this distribution of this product is just this action. So every time I have to define this, I have to say how it acts in some test function and what number it gives, and is this number. And you see that this, for instance, if this distribution comes from a function, so it's a t of f, then this in here is what you expect. So it's f times 5 times phi, which is t of f of this product, which is also, you can take these two, t of 5 times f times c. So in that sense, it's a product. And so, but you cannot take a product of two arbitrary distribution, doesn't make any sense, okay? So the only thing you can do is multiply by distributions coming from test functions. Now you can take the derivative. You can define derivative and make equations on distributions. And the derivative is like this. Suppose you take a t of a function, which is continuous, say, or differentiable. Then your t of f prime will be applied to a phi, will be, by definition, f prime times phi. And so here we can integrate by parts, because these two functions are differentiable. And the boundary is 0 because this is compact support, so I can change this derivative to here and put a minus. So I get this. And this is minus t of f of phi prime. So the idea is now you define the derivative of a distribution acting on phi as the number minus t of 5 prime. Okay? So this is a definition. I need to tell you how t prime acts in every test function, and the number that gives is this, which is well defined. Okay? So this is the definition for all phi belonging to the test. So this is what we meant by a derivative. So for instance, if you take a t of f where f is only integral, so not even continuous, there is no problem. I can take the prime of this, and this is just minus the integral of f times phi prime. Sorry. And this is well defined because this function is differentiable, and this is integral, so this product and this integral is well defined. So this is okay. But notice that the derivative goes into the test functions, right? So this is okay. And so this is a way of considering, okay, if I have just a function that is integral only, and I say, what is the derivative? Well, you say, oh, this is a distribution in this sense, and taking the derivative of that is another distribution, and is this distribution, okay? So we know how to take derivatives, and so we can write equations. For instance, I could write the equation let's say f prime equals to whatever, lambda f right? Our nice ordinary differential equation. I can say, okay, this is, for functions, this is true when this function is differentiable. But now I can say, okay, I have this thing here, I multiply by a phi, I integrate, and this I integrate by parts, this term, and this is minus phi prime minus lambda phi times f dx is 0, okay? And so this is the way we see this, and this is, if we write down as an equation, right, we get t of f prime has to be equal to lambda t of f, okay? And this way of writing things is just that. So this is for all phi. So the question is, find f such that this is 0 for all 5. And f is a distributional solution of this equation in this sense. The distribution I get is tf. This is the solution, okay? So this is very convenient, because if you follow the definition of distributions, etc., there is no problem understanding what people do when using delta functions and derivative of delta functions and things like that. They are all okay in the sense if you use the definition. So you always multiply everything by a test function and integrate, and then everything is fine, is well defined. So here is to show that the prime operator is acts on vector spaces. So if you take the prime of this linear combination of two distributions, apply to phi, do the definition here, split these things into phi here, and regroup this, use the definition back, and you get that the distribution of a sum of the derivative of a sum of distributions is the derivative, the sum of the derivatives. And it also satisfies the Leibniz rule as much as possible. Remember that we can make product of a distribution times a distribution with a regular distribution that comes from a test function. So we can take this product and take the derivative of that, and by definition this is minus this, and this by definition of this is this product here, and this product you can write, this one you can write as a total product, the total derivative minus the other derivative, and this is t twiddle of this, and this is t twiddle of this in here, so you split, and this here you can take to write this as going back to the t, right? So this t phi times this to the product, definition of the product, and this part also you can do the same. So this, you take the 5 out this way, so you get the t phi times t prime, and so you get this. So it's a Leibniz rule. So here the distribution acts on t prime, and here acts in this, because this is with here I think I have a wrong sign. Okay, I don't know. I think there is a mistake here. Okay, I'll check later. So you can take, for instance, the derivative of the delta function. T prime of A. So by definition, this action of phi should give me minus T of F of phi prime. And this is minus phi prime of A. This is a result. So this is a derivative of delta function. Okay, so as distribution you can take derivatives of whatever you like. And here there are many more examples. I want to check. Here is the corresponding theorem in distribution, that if you have a function, then there is always another function, so this is the integral of g, okay? And this is the way you do it in distributions. So you can carry many things of equations to distribution. In particular, when we are doing, let's see where I can write here. I want to, this is all. Let me write here. In particular, what we are doing is, when we say, okay, suppose I have this equation. And I can extend this to distributions. Say, okay, I want to take a derivative here of a distribution equal to. So what this means is that I want to take, let's say this equal to 0. I want to apply, so this is a distribution now. So apply to a function phi, any function should be 0. So I'm just looking for this. But this is just t minus t of phi prime in the direction of t. So here we are in R2, right? Distributions in R2. Let me write it better. This here is minus the integral of t of, sorry, I don't want to use integral yet. So this will be minus t to dt of phi, and the other one is going to be plus t to the x of phi. Okay, so this is t to the t phi minus dx of phi. Okay, equal to 0. So this should be a distribution such that if I apply to this, it gives me 0, right? So it might be that the solution is a function. So if I look at t of f and I say, okay, is there a solution of this type? Then this equation is nothing else than minus f times dt of 5 minus phi x 5 equal to 0. Huh? So you see what you are saying is, okay, find a function whose distribution is a solution of this, okay? And if it is a function, then the solution is log. So that's what we say, that this f is in the distributional sense a solution of this equation, because we are thinking this way. So once you get this f here, then you get a distribution. And this f might not be even differentiable, okay? So this is what we say. So there are two levels here. I can say, okay, I have a distribution in general, and I have this equation, and I look at as this equation, this means this. So find a distribution that satisfies this. And this could be many things, really very bad in the differentiability, depending on what initial data you give for this. All right? Can be in many subspaces with for instance, a solution of that could be delta of t minus t plus x, I think. For instance, this is a solution of this, okay? But you can say, okay, it might be that the distribution, the solution is of this type, so it's a distribution that comes from a function. And this function can be differentiable, and it's then I can integrate by parts and get the usual solution, or it could be just continuous, or it could be distribution integrable, or it could be like this, right? There is no problem. So these things are all solutions of that equation in the distributional sense, and which one you get depends on the initial data, right? So this is how one opens the class of solution of an equation. Say, okay, I will consider distribution. Of course, all this works in this generality only works for things which are equations that are linear. So I can use this. At most, I can use for things like the one we were seeing, that where we have a t phi times another distribution. Things like that I can include, but no many more things, because in general there are no products. So for instance, if I have an equation like the ones we were looking today, which are linear equations with variable coefficients which are with some differentiability, then you can extend the solutions to weak solutions, to differential, to distributional solutions without any problem. Because when you have distribution, you know how to sum things, derive things, etc. You have derivative of distribution. You have all the calculus for distribution. So they are well defined, the space is okay, etc. So mathematically it's okay. And sometimes what we are seeing now is that it's easy to find solutions in some class of solutions, distributionals, which is bigger than the class of continuous functions or differentiable functions, okay? So that's why it's interesting to extend this. Okay, so I will stop now if there are questions, and otherwise I will stop and we will look at the homeworks, because there were some questions on the homework. Are questions? Any question? Okay, here there are two. Virginia, the distribution then are those used in relativistic physics when a metric space is not possible, or the charge density analyzed with Dirac delta. Yes, for instance, this equation that we use for instance in electromagnetism, you use this equation. Right. This equation you have to understand it as distributional. Right. The solution is 1 over r, and 1 over r is not differentiable at r equal to 0. So you have to understand as a distribution. So the right way of looking at this is distributional. Okay, Felipe says, during the course, will we see nonlinear dispersive anticipative systems? Yeah, we might try to see. Now with the tools, for instance, for dispersive and dissipative systems, so they don't have shocks in general, you can use now the finite difference scheme and solve whatever Corte debris or whatever you want to solve. You can even solve Schrödinger's equation. You have to be careful with Schrödinger's and how you integrate it, but you could solve it also. But so now you have the tool, right? we know how to solve this dx of u when we substitute this by d, but we can use just, for instance, if you want to solve dt of u equals to, I don't know, dx of u, dx x of u, say this. I think you can solve this. Then you will do this, and here a second order operator. You can do many things and then use Runge-Kutta. So now you have a whole slew of solutions you can solve. After lab 4, lab 2, you can do a lot of these things. Maybe we can include some at the end of lab 2, some examples or some system that you can choose and play with them. I think that will be good. By the way, we should be getting tomorrow. You will get lab 2, so that maybe tonight I'll try to finish it, so that you can play with lab 2 tomorrow already. What we cannot do now is to solve for shocks, but for evolution equations, including parabolic equations, etc., you can use this method, finite difference. And we have to learn how to do boundary value problems, but that we'll do, maybe we'll start tomorrow. Okay, let's go to the homework.